Okay, good evening, everybody. And welcome to another session of organic chemistry. Okay, in today's session, we are going to finish chapter 7. Yeah, we are going to finish chapter 7. Essentially, we will be discussing electrophilic addition reactions. And I'm sure you guys also want to go over the quiz that you have just taken. Okay, so let us do that before we get this session started. Okay. Okay, Tiffany, go ahead and read this question first. Okay, name the following alkenes. Okay, what is the name of this molecule here? Okay. How do you number it? Let us number first. How do we number this? Where is 1? Right here? Okay, good. Where? Right here? Okay, why? Okay, why don't we make this 2? Oh, okay, very good. We were just checking. Okay, that's 3, and this is 4, 5. Okay, so the name is therefore. Can we have some quiet, please? Okay, Ryan, go ahead. 1,5-dimethyl cyclo 20. Okay, very good. Okay, so that is the name for this molecule here. About this one here. Yes. Why can't we make this number 2? Why can't this be number 1? Okay, because we told you earlier that whenever you have a carbon-carbon double bond and an alkyl group is attached to one of the carbon of the carbon-carbon double bond, that carbon has to be number 1. Okay? Okay. So about this one here. Okay, so we number 1, 2, 3, 4, 5, 6, 7, and 8, right? Okay. So what do you call it? 1, 5 cyclo octa, exactly, for 8 octa. Then you have the diene, right? Okay, very good. So you guys are ready for nomenclature, yes? We say when you have a ring system, you don't need to indicate the position of the double bond. Yes. That's for the straight chain. That's for the straight chain. Okay, now that is the wrong. Okay, now, Alfreda, go ahead and read this first. Yes. Okay, thank you. Okay, so what we want to do here, right, the IUPAC name for each of these the following compound here, this compound and this compound, including the easy stereochemistry. Okay, so let me go ahead and erase this. Okay, so what would this be? What is it? What is the let's number? Where do we start numbering? From here? From here, okay. From where? From here? From here? Okay, so we start from here, right? Okay. 1, 2, 3, 4, 5, 6, and 7. So that is the longest carbon chain is 7. So therefore, where are the branches? Where are the branches? 3 and 4. You have branch here in the 4 position and also in the 3 position. Okay, so it becomes. Okay, what would be the name? No priority, right? Yeah, that's true. That's true. Okay, so let us give the priority between the metal and the hydrogen. This is A, and this is B, and here B and A. So therefore, that would be what? E. So the stereochemistry here is C. So what would be the name? 5E, 3,4 dimethyl penta eta 1,5. Is it penta or hepta? Hepta, okay. So it becomes 1,5 heptadiene. Very good. 1,5 hepta. Then the di and the ene. Okay, very good. Yes. Because you have to name such that the carbon-carbon double bonds will be given the lowest combination of numbers. Okay. And you could try it yourself. You find that if you went the other direction, the number will be higher. Okay, what about this one here? What is the longest carbon chain? 7. Where do you start counting? Right here. 1, 2, 3, 4, 5, 6, and 7. Okay, so 7 carbon here. Okay, the branches are where? 3 and 4. You have a methyl branch in the 3 position and an ethyl in the 4 position. Okay, I think you guys already have the nomenclature down to a science. Okay, so what would be the name? 3Z. Okay, in this case, you don't necessarily need to indicate the position of the stereochemistry, so if you say Z, but if you say 3Z, that's fine. 4 ethyl, okay. 3 methyl. Okay, 3 F-ene. Very good. Yeah, you have to. For the straight chain. For the straight chain, you got to indicate the position of. Yes. Yeah. It's only when you have a ring that you do not have to indicate the position. Okay. Okay, very good. Okay, so let us go to the next one. Okay, so we don't have to do this. Okay. Okay, so let's do 4. So by the way, the answer to this is 7. 4. Let's see. Area, can you read it for us? Can you see it from the back? Area, can you read number 4 for us? Yeah, go ahead. Say what? Oh, Jeanette, go ahead. Read it. Read number 4 for us. Okay, thank you. So it says write the structure for the following IUPAC names. Okay, so you have 3E5Z26 dimethyl 1357 octa tetra in. Okay, what would that look like? The longest carbon chain is what? It's 8. Okay, so we have okay. Now in the you have the double bond in 1, 3, 5, and 7 position, right? So if you say this is 1, that's 1 double bond here. 3, let's number them so it will be obvious to you. 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So you have 1, 3, 5, 7. So far in the carbon number 5 you have a double bond, and then carbon number 7 you have another double bond. Okay, so we're taking care of the double bond. Then on the branches you have branches where 2 and 6 position. So you have a dimethyl, right? Two and 6. Okay, now so we now fill in the rest with hydrogen, right? Now before we do that, we in the 3 position, the double bond in the 3 position, the stereochemistry is E. So which is this one here, right? Okay, so if it's going to be E, I will have to place the hydrogen here. Alright? And then the other hydrogen here. You see that? Okay, and the 5 position is Z. So that means I place the hydrogen here. And this one here. Oh no, I'm sorry. Take that back. Okay, if it's supposed to be, then where should the methyl be? Oh, very good. So I need to take this out of here. So at this point, I just fill up the rest with hydrogen. Hydrogen here, 2 of them. We have 1 here. It's okay. It's okay. It's okay. You have 2 here. Okay. Now, do we need to show stereochemistry for the 1? No, we don't need to do that. Why? Exactly, because you have 2 hydrogen attached to this carbon here, and the same thing applies to this position here. Okay, very good. So that would be the structure they wanted to write. You could do this using the skeletal structure. That's fine, or a combination of skeletal structure and semi-condensed structure. That's fine. Okay, so that is A. How about B? B. Oh, you go ahead and read B for us. What is B?
6,3,3 dimethyl 4-propyl 1,5-octadiene.
Okay, so we need to give the structure of 6,3,3. Thank you. 6,3,3 dimethyl 4-propyl 1,5-octadiene. Okay, so what is the longest carbon chain? 8. Okay. Okay, so you have 8 carbon, and in the 1,5, you have double bond in the 1,5 position. If we say this is the position number 1, so there's a double bond here. So 2, 3, 4, and 5, right? So another double bond here. Okay, then let us fill in the rest. The branches are where? 3 dimethyl. So we have, in the 3 position, you have 2 methyl. And in the 4 position, you have propyl. You have propyl, yes. And what is propyl? How many carbons? 3. Okay, very good. Okay. And then, so that's all, everything. We just need to fill up with hydrogen, all right? So here we don't have to worry about the 6 strands on that carbon-carbon double bond. Okay, but here we fill this up. This is CH2. Now, if you do this, do not forget to fill in with the hydrogen. Okay, now we want to focus on, just a minute. We want to focus on this carbon-carbon double bond. It's supposed to be 6. So where would the hydrogen go? Remember, we are looking at 6. Where would the hydrogen go? On the same side of the double bond, right? Yeah. Okay. So we could simply place the hydrogen here and hydrogen here. Yes?
Why isn't the CH on that side, on the left side? Why isn't the CH?
Where? In this here?
No, the left side, all the way farthest left side. Oh, I'm sorry, my left.
Oh, I'm sorry.
You're right.
Yeah, no, that's fine.
Okay.
It's my left too. It's my left here, yeah. Okay. Okay. That was an error. Thank you. Okay, so that is the correct structure. So in this case, we have a cis stereochemistry at the carbon-carbon double bond, which is in the 5 position. Okay, so I think that's about it. So any question before we move on? Yes. So everything will be at 12 points. But I only wanted to do 3. So I will take the first 2, since everybody get credit for number 3. Okay. Okay. So let us go to today's lecture. Which one? Okay, so what I want to do today, I want to begin the organic chemical reactions. Most of the semester so far, we have been laying the foundation for the introduction to organic chemical reactions. So today we are going to start. Essentially, in organic chemistry, you have 4 major types of reactions. 4 major types of reactions in organic chemistry. And we have what we call the addition reaction. Just as the name suggests, in this case, we take a carbon-carbon double bond. We are adding, in this case, hydrogen and bromine across the carbon-carbon double bond. So you get an addition product. So it says addition reaction. So anytime we say addition reaction, in other words, we have 2 molecules, we are adding them together. And then we have what we call the substitution reaction. In the case of substitution reaction, you will also see variations of this. in essence, if you take a look at what is happening here, we have this molecule here, methane, reacting with chlorine, and we are replacing one of the hydrogen atoms with chlorine. So just as the name suggests, that is exactly what we are doing here, replacing one of the hydrogen atoms with chlorine. So this is a substitution reaction. Of course, there are some other types of substitution reactions, but this is just an overview of the major types of reaction you will encounter in organic chemistry. Then we also have what we call the elimination reaction. In the elimination reaction, just as the name suggests, we are eliminating some fragment out of a given molecule. In this case, we're starting with this molecule here, which is ethyl alcohol, ethanol. Starting with ethanol, and in the process of the ethanol reacting with some kind of acid catalyst, we will be eliminating water, and therefore we form an alkene. You see here, so we therefore refer to this as elimination reaction. So anytime you are eliminating a small molecule from a bigger molecule, we refer to that as elimination reaction. So there will be different variations of this type of reaction as we go along during the course of our study in organic chemistry. And then finally, on this slide, we have what we call the rearrangement reaction. Rearrangement reaction, just as the name suggests, what are we doing? Rearranging. See, the organic chemists are very innovative, and they come out with all these fancy names. Okay, so we are rearranging. So what are we doing here? If you notice what is going on here, we're starting with this alkene, and we're forming another alkene right here. So in other words, we are going from one isomer to another isomer because both of them have the same molecular formula. Nothing is being lost. All we are doing is rearranging the position of the carbon-carbon double bond. That's all we are doing, and then of course rearranging the molecule. That's essentially what it says. So these are the four major types of reactions we are going to encounter in organic chemistry. There is also an additional reaction that I want to know, which is also very important. Want to go back? Yes. Right here? Yes, that is CH3, CH2, right. Okay, so we are rearranging from here, from this alkene to this alkene. Okay, so there is another type of organic chemical reaction that is also very important. Let us call it number 5, since we've given you 4 types of major types of organic reactions. It's what we call the acid-base reaction. Acid-base reaction. Now for the acid-base reaction, you could imagine, say for example, bless you. Say I have this molecule here, which is hydrogen chloride, and then I have this water. We could get a reaction between the hydrochloric acid and water, to form what we call hydronium ion. And we very often write this as this. So we are going to be using this very often. So you see us write hydronium ion. So anytime you have a solution of water in dilute acid, this is what you form, hydronium ion. Of course, you also form the chloride anion. This is an example of an acid-base reaction in which, in this case, this is the acid. This is the base. Of course, this reaction is an equilibrium reaction. It could go back and forth. And in this case here, this will be the conjugate acid. Change the color of my pen. So the hydronium ion is a conjugate acid for this particular reaction. And of course the chloride anion here, this is the chloride, is the conjugate base. So we say this is an acid-base reaction. Now I bring this up because I want to use it to introduce some of the mechanism that happens in organic reactions. Now in this particular reaction here, what is happening? What are we doing? We take the hydrogen chloride. What does it do? Attract the bonding electron, the pair of bonding electron to itself. So in essence, what do you have? We form a proton. And in the process, we form the chloride anion. This type of cleavage, chemical cleavage, in which you have a bond between two atoms, and there's a bond breaking, and one of the atoms attracts both of the bonding electrons to itself. We refer to this as heterolytic cleavage. In other words, in most of the chemical reactions that we are going to encounter, this is the kind of cleavage that is going to occur, in which one atom is attracting all of the bonding electrons to itself, and the other atom, of course, will now be positively charged. In this case, we now form the proton, and then we also form the chloride anion. So this is one type of what we call the heterolytic cleavage, or sometimes referred to as heterolysis. There is also another type of cleavage in organic chemistry that we are going to encounter, and that is what we call the homolytic cleavage. In the homolytic cleavage, imagine that you have two chlorine atoms in the presence of light. what happens, instead of one of the atom pulling both of the bonding electron to itself, what happens, the bond will break so that one electron goes here and another electron goes here. In this case, you are going to form keep in mind you have the non-bonded electron on chlorine. So in this case, you are going to form what we call free radicals. And free radicals are very, very dangerous intermediate reagents indeed. I'm sure you've heard of free radicals before. These are the kind of intermediates that cause cancer. In other words, you really do not want it in any kind of system, because they are very reactive. Okay, so therefore, the point to be made here is we have two types of cleavages in organic chemistry. One is homolytic cleavage. What happens in the homolytic cleavage? The bond breaks in an asymmetric fashion, in which one of the atoms takes both of the electrons, right? Yes, in the heterolytic cleavage. Okay, just this here. This is the heterolytic. Oh, that's what okay. Sorry about that. Okay, but in the heterolytic cleavage, what happens? Okay, the bond breaks and one of the atoms takes both pairs of electrons. So that is heterolytic cleavage. In the homolytic cleavage, the bond breakage this is the homolytic right here. Okay. Okay, so now, before we get into the other chemical reactions, there are some other terminologies I want to share with you. Yes. Yes. Both of the atoms will take one electron each. Okay, keep in mind in any covalent bonding you have two electrons. So in the homolytic cleavage you have a symmetric cleavage. In other words, one electron goes to one atom, the other goes to the other atom. Okay. In the heterolytic, that is asymmetric cleavage. Okay. There are a couple other terminologies I would like to share with you. If we have this, go back to water again. Remember, we just told you that water could act as a base. We could also say that water could act as a nucleophile. What is a nucleophile? Phile means to like, to love, right? So a nucleophile means what? A nucleus lover, right? So in this case, water could also, in addition to water being able to act as a base, it could also act as a nucleophile. So therefore, you want to ask, what is a nucleophile? A nucleophile is any species that contains either pi electron or non-bonding electrons. Which is to say that if you have a carbon-carbon double bond, you see where I'm going here, since we are dealing with alkene. If you have a carbon-carbon double bond, the carbon-carbon double bond, the pi electron in the carbon-carbon double bond could be a nucleophile, could act as a nucleophile. So we could say this pi electron here could be nucleophilic. In other words, it could act as a nucleophile. Just as the non-bonded electron in water will act as a nucleophile. The pi electron in the carbon-carbon double bond could also act as a nucleophile. So we say it is nucleophilic. In other words, it is looking for a positive center, or a proton in this case. In some cases, proton, but in many cases it could be a positively charged species that it is looking for. Okay, so we have what we call nucleophile. Then we also have the opposite of this, electrophile. Now the electrophile simply means something that loves electrons. So what would be an example of an electrophile? For example, it would be a proton. The proton could be a good electrophile because it is looking for electrons. If you have an intermediate molecule just like this, in which you have a formal charge of +1 on this carbon here. This carbon here, we could also call this carbon an electrophile. Or we could say it is electrophilic. In other words, it is looking for electrons. Now, this type of intermediate here is what we call a carbocation. And this is going to be a very, very important intermediate for the most of the rest of this semester. A carbocation. So you're going to hear us say carbocation, carbocation. You get so tired of it because it's also a very reactive intermediate. Okay, a carbocation therefore is any species, intermediate species that has a positively charged carbon atom. Okay, any intermediate species that has a positively charged carbon atom is a carbocation. Okay, now why did I say all of this? Now I want to get to remember I told you that we are going to discuss electrophilic addition reactions of alkenes. So let us now get to study reactions of alkenes. Okay, electrophilic, let us call it electrophilic addition reactions of alkenes supposing I have this molecule here. I have cyclohexene. We all know cyclohexene by now. And I have hydrogen chloride. The pi electron in the cyclohexene is nucleophilic, looking for a positively charged species. And the hydrogen that is attached to the chlorine could become positively charged and therefore become electrophilic. In other words, looking for electrons. So what will happen? Okay, so you could have this pi electron here. Notice what I'm doing here. Attacking this proton. In so doing, to help to break the hydrogen-chlorine bond in an heterolytic cleavage. Remember we said heterolytic. I also notice what I am doing here. When you draw this arrow, every time you draw arrow in organic reactions, that is showing you the flow of electron. In other words, what we are saying here, electron is flowing from this pi electron to this proton. Okay? In other words, electron will always flow from the nucleophile to the electrophile, not vice versa. Okay? So therefore, what do we have? So we use the arrow to show what is happening during the course of a chemical reaction. In this case, we have this here. Okay, let me simply show that this hydrogen is green. Okay, so the hydrogen is here, and the other hydrogen is here. It's still there. And now, what is going to happen to this carbon right here? Would there be a formal charge? Keep in mind this using this pi electron to attack itself to this proton here. Okay. What is going to happen to this carbon? It becomes positively charged, right? Okay, so it becomes a carbocation. Becomes a carbocation. Yes. What is it? Say that again. If you look for the formal charge, let us know. Remember we did formal charge? Okay. If I just have it this way without the positive charge, okay, you have to calculate the formal charge for that carbon. But to make it easy for yourself, in essence, if you look at this pi electron here, we say we are moving this pi electron, moving it so that this carbon is going to attach itself to this. So if you are moving electron away from this carbon, it has to be positively charged. But if you want to go down to what we did much earlier, you could simply calculate the formal charge. It will be +1. Okay? Because here you have only 3 electrons belonging to carbon here. Remember we said formal charge will be the valence electron minus the number of electrons that belong to it. That's 4 minus 3. In this case, that would be +1. So you have +1 here. Okay, anyway, so we have a carbocation here. In this case, we call this a secondary carbocation. Why do we call this a secondary carbocation? Why do we call it a secondary carbocation? Because what kind of carbon is it? What is a secondary carbon? Attached to 2 other carbon atoms, exactly. So therefore, a secondary carbocation simply means that this carbocation, that carbon is attached to 2 other carbon atoms. Now, do not forget that we also have the chloride anion is here. Since this is breaking away and forming this chloride here. So what we have here, we have a carbocation that is formed as an intermediate product, and we also have the chloride that is formed. And what is going to happen, this carbocation now will be acting as what kind of species? Exactly. Will be acting as an electrophile, looking for electron. And the chloride anion will be acting as a nucleophile, looking for a positively charged center. Keep in mind, any positively charged center we will refer to as being electrophilic, in other words, to attract electrons. So here, this is the nucleophile attracting this electron to here. So I will draw an arrow again. And so the next process of what we have here, take this out of here. Secondary carbocation. So the next process is, we have this. So the next process is what? This is the final product. This is our final product. So the next process is the addition of hydrogen chloride to the carbon-carbon double bond. Now, what I've given you here is what we refer to as reaction mechanism. What I've given you here is what we refer to as reaction mechanism. So that in the reaction mechanism, what does it do? We show you the step-by-step of how a reaction takes place, starting from the starting material to the product. So if I tell you, write the reaction mechanism for me, I expect you to be able to show me how this reaction occurs by showing the arrow. Essentially, you got to draw the arrow to show the movement of electrons between all of the reacting species. Okay, so in essence, the product here is addition of hydrogen chloride, and therefore we refer to this as electrophilic addition. Why do we call this electrophilic addition? Because the first step of this process, what are we doing? We are adding this here, the hydrogen, which is the electrophile. Because the first step of this process, of this reaction mechanism, it is the addition of the electrophile to the carbon-carbon double bond. And so therefore, that is why we call this electrophilic addition reaction. Okay? Now, if you were to write a reaction profile for this, reaction energy profile should be reaction energy. Imagine that you have this is energy right here. This is the time. You say you have your reactant here. It goes through a transition state, forms an intermediate carbocation, and then you go to another transition state to form your product. So you have your starting material here. In this case, we have the alkene plus the HCl. Now the apex of this peak is what we call the transition state. So in this particular reaction here, we actually have two transition states. So let us call this transition state 1. And this here, the second one is transition state 2. And the energy here. The energy difference between the starting material And the transition state 1 is what we refer to as the energy of activation. We refer to as energy of activation. In other words, that is the amount of energy that is necessary for this reaction to occur. In other words, we got to supply the energy. Once you supply the energy, maybe in form of heat or pressure or whatever, the reaction will occur. And then right here, you now form this intermediate. You form the intermediate carbocation. Change my pen here. You form your intermediate carbocation right here. So if you see any reaction energy profile looking like this, what this is telling you is that this reaction is going through an intermediate. In other words, the initial process go to the transition state collapses to form an intermediate, and that intermediate at this point will now react with another species to get to the final product. So in this case, this will be your final product right here. What drives this process, therefore, is the fact that the energy of the final product is much less than the energy of the starting material. You see here, if you look at the energy profile, in other words, the product is a lot more stable. And that is what happens in a lot of reactions in organic chemistry. What generally drives the reaction is the fact that the product is a lot more stable than the starting material. Okay, how much time do we have? Okay, we've got plenty of time. Okay, now, so what I've done is to give you the mechanism of electrophilic addition reaction. Let me repeat that again because it's a very important process. Supposing I have this. Supposing I have this. And I say this reaction is taking place, hydrogen bromide, and I ask you to give me the mechanism of this reaction. Of course, this is what I was expected to give me. You have this acting as a nucleophile, attacking the proton right here. In so doing, you break this heterolytically, and then you form an intermediate. Plus the bromide is here. You form the intermediate. Now, what kind of carbocation is this? Primary, secondary, tertiary? Primary. So in this case, we form a primary carbocation. And now what happens? So this is the intermediate that is formed. Now what happens? The bromide now comes in as a nucleophile, attacks this, you form the final product. So the next process here is the addition of hydrogen bromide across the carbon-carbon double bond. Okay? That is the next process. Now, it isn't all the time that I will be asking you to give the mechanism. Supposing I just ask you to do this. Supposing I just do this. And I say, give me the product of this reaction. Okay? Say, give me the product of that reaction. What would the product be? Keep in mind, I'm not asking for mechanism now. Give me the product. Yeah, what did it be? We are adding hydrogen and bromine across the carbon-carbon double bond. That's what we're doing, right? Okay, so what will it be? Where would the bromine go? On this here? On this here? Is that right? You think so, eh? Okay, let us see. So you say it will be here. So you are telling me now this is the product, right? Well, where the hydrogen is here, okay. Don't forget the hydrogen was here before. So you're saying that is the product? Okay, that was really a trick question. That is not the product. No, it is the right product. I was hoping that you would tell me otherwise. Now, but that is correct. That is the product. Okay, that is the, now. What is the mechanism of this reaction? No, this is correct. This is correct. But why is it? Why is this correct? Why not? No, why not this? The question is why not this here? Why not this here? Why not that product? Why not that product? Why not? Because what? Okay. Okay, now, okay, I think you guys just took a nice guess. That was good. This is the right product. But this is the answer to that. If you give the mechanism for this reaction, what is going to happen? This pi electron here is going to attack this. Whenever you perform an electrophilic addition reaction, keep in mind that you are forming an intermediate carbocation. Whenever you form an intermediate carbocation in any reaction, the most stable carbocation will always be formed. Keep that in mind. The most stable carbocation will always be formed. So in this case, we are going to form this. We are going to form this carbocation. We add hydrogen to this carbon here, and the carbocation will be here. And that is a tertiary carbocation. This is a tertiary. Okay, now once you form the tertiary carbocation, of course the bromide that is formed, which is here, will now attack the tertiary carbocation to give the product. That is how this product is formed. Now the question is why that is so. Okay, what I want to do now is give you the order of stability of carbocation. Order of stability of carbocation. Okay? The most stable. Let us use R. Most stable. In other words, in any chemical reaction, if the reaction has a choice of forming a tertiary carbocation or a secondary carbocation, that reaction will go through the process in which a tertiary carbocation will be formed. Okay. 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 Tertiary carbocation is more stable than secondary. Okay, more stable than primary. And more stable than primary is more stable than methyl. Okay, so of all the carbocations, at least for now, I will give you some other examples of carbocations that are stable later. the tertiary carbocation is very stable. Okay? So therefore, if a reaction, what I told you before, let me write it down for you. If a reaction has the choice of going through a carbocation intermediate, going through a carbocation intermediate, the most stable carbocation will be formed. The most stable carbocation will be formed. The most stable carbocation will be formed. Yes. If a reaction has a choice of going through the formation of a carbocation, in other words, carbocation is an intermediate. In that case, that reaction will, if it is possible to form the most stable carbocation, that is what will be formed. And that is important in being able to determine the outcome of chemical reactions. Electrophilic, at least with regard to electrophilic reaction to alkene. So therefore, supposing I give you this here, I ask you, what is the product of this reaction? What is the product of this reaction? What do you think the product will be? Yes, Paris. Let's call this carbon 1. Let's call this carbon 1 and this carbon 2. Keep in mind we are adding hydrogen and bromine across those two. So where will the hydrogen go? Okay. Why? Okay. In other words, you're saying this is the product, right? And I think you are right. You are saying this is the product. Right? Is that what you're saying? Yes. Okay. That is correct because you are forming the more stable the tertiary carbocation. Yes. And by the way, this type of reaction is what we refer to as Markovnikov reaction. Markovnikov. And what does Markovnikov reaction tell you? Anytime you are performing an electrophilic addition reaction using a carbon-carbon double bonds, the hydrogen will always go to the carbon that has the most hydrogen. Okay? Anytime you perform electrophilic addition reaction, the hydrogen atom will always go to the carbon that contains more hydrogen. What do you mean by that? Look at this reaction here. Where does the hydrogen go? The hydrogen goes to here, because this carbon contains more hydrogen than this carbon. So that is the way in which you could determine the outcome of this reaction. In other words, this hydrogen here comes here because this carbon contains more hydrogen. Okay? So therefore, the last one before we go, just the last one. One more, just this last one. Okay, so according to Markovnikov reaction, what will be the product of this reaction? What will be the product of this reaction? Exactly. So that is Markovnikov reaction. We call this Markovnikov addition reaction. Okay? Because in Markovnikov, the hydrogen is added to the carbon that contains more hydrogen. Okay? In Markovnikov, addition reaction, the hydrogen is added to the carbon that contains more hydrogen. Okay? And that is the end of. We will continue chapter 7 on Tuesday.
So wait, is Al still being presented, or is he finished?
Yeah, you got enough information to finish out. Okay, so we will finish our chapter 7 on Tuesday, and then start chapter 8 also on Tuesday.
Wait, don't keep that. You said okay.
Okay.